Hello, we're back. So let me do a quick review. So where we left off, and I did fix the slide, you can see here. So number of electrons are fewer than the number of protons for positive ions, and electrons are greater than protons for the negative ions. So this is video number 2. And so what I'd shown you is that an atom compared to an ion, right? Very, very different physical properties and very, very different chemical properties. So interestingly, if we change the number of electrons, the properties change significantly. Now, isotopes are defined as atoms of the same element with different numbers of neutrons, or you could say different mass. And you can remember it either way, because if they're the same element, the number of protons have to be the same, but if the mass is different, it must be the neutrons, because electrons have a very, very small mass. All right, so this is an example of isotopes. These are isotopes of phosphorus. This is called P30 and P32. And you can see they're both phosphorus, so they both have 15 protons. This one has a couple more neutrons. Now, I don't have any videos on this because there's not much to see, because isotopes have nearly identical properties. Nearly identical. They differ only in mass, and if they differ in mass, of course, we talked about density before. If the mass is different, the density will be different. Pretty much it's only the mass and density that all have different properties. All the other properties are the same except sometimes radioactivity. And the reason I say sometimes is there may be more than one isotope and none of them are radioactive. And we're going to talk about radioactively extensively if you look ahead in the Canvas shell. But just very quickly, radioactivity is when an atom falls apart. And when it falls apart, it gives off a lot of energy. For that reason, the atoms can be detected, the energy can be used for things, but since the other properties are similar, they do all the same, all the chemical properties, they do the same reactions. So radioactivity can be used for a number of things, but it can be used to follow processes. Since we can't see atoms, but we can detect radioactive ones. You can do an experiment, for example, P32, the one I showed you. P32, DNA contains phosphorus, and if you want to detect DNA, you make DNA with radioactive phosphorus, and then you can figure out where it went. Okay, so it can be used as a tracer, things like that. Right? Some of you may have had a medical diagnostic procedure where they gave you a radioactive isotope, and then they would do some imaging, and that's because the radioactivity will help them see it better, and they can get some nice images of things they can't see, and because it's similar or the same element, it will do all the same reactions. So radioactive potassium would go where normal potassium would go. All right, but isotopes, basically the same element, different mass. All right, so just to put this together, isotopes, same element, different masses, so they differ only in the neutrons, right? Structurally, what's different? The neutrons. Very similar properties. Ions are charged, very different properties, which I showed you. Structurally, what's different in ions? You guessed it, the electrons. So what does this suggest? It suggests that if you change the number of neutrons, well, what changes if we change the number of neutrons? Almost nothing. But if we change the number of electrons, you'll see what changes? A lot, right? And this suggests that neutrons aren't terribly important to the behavior. Change the number of electrons, we change both the physical and the chemical properties. That means what the electrons are doing has to be much more important to the behavior. Right? So in chemistry, structure-function relationships are extremely important. If someone says, think like a chemist, they're telling you to think in terms of the structure and the function, because chemists believe that the structure and function are related. And you'll see that thread all the way through this semester. So if we relate this to the structure, all right, it turns out, structurally, the protons and neutrons are in the nucleus of the atom in the middle, and electrons are in what's called an electron cloud surrounding the nucleus. And we think of it as being in layers, so concentric clouds. The outermost layer is called the valence. I don't know where the word came from, but that's what it's called. Very important, if you've ever been taught that electrons orbit the nucleus like planets around the sun, you need to unlearn that, because it's just not true. It's an oversimplification that is wonderful for maybe even high school, but it's not good enough, really. And there's a lot of reasons for that, but they don't do that. They're just kind of, we say clouds because clouds have fuzzy edges. They're just in layers. So if we look at this, this is a nice picture. So the protons and neutrons are here. And these are the layers. So there's 2 electrons here, there's 4 electrons here. They're not moving in any particular path. Right? This one would be the outermost layer, this would be the valence. And if you look, see if you can figure out what element this is. There's 1, 2, 3, 4, 5, 6 electrons. See if you can guess. That's right, it's carbon. All right, now, why we relate this to function? Remember, if we change the electrons, it makes a big difference. If I take, for atoms to react, they have to bump into each other. If the atoms bump into each other, what parts of those atoms are going to hit? The outside, right, the outside. And what's on the outside? The electrons. So what those electrons are doing out there is going to be really important. The neutrons are in the center, right? They're in the middle, so they're never going to encounter each other. Okay, so and we saw isotopes don't have very different behavior. All right, now I'm going to show you how to use the periodic table. So the secret to the periodic table is that the periodic table is a map. And that map will lead us to knowledge. So first of all, this is a periodic table, and you'll see this darkened stair-step line here. That's kind of a nice little line. And this is a very simple periodic table, but it's a good one. All right, so first thing, there's a couple of different types of elements. There are metals, there are nonmetals, and there are metalloids, although for this class, metalloids aren't terribly important. All right, metals, all metals have metallic luster. What does that mean? It means they're shiny. Now, if you look at the surface of a metal, it may not look very shiny, but that's because a lot of metals, most metals, will react with oxygen in the air, and they form metal oxides. You're familiar with rust, which has an orange color. Most metal oxides are black, white, or gray, though, so metals will look kind of dull gray or even black. Okay, metals are malleable. So malleable, that's the same root as mallet. That means if you whack a piece of metal with a hammer, you can make it into thin sheets. They also will conduct electricity. Okay, some other things about them, right? And metals are to the left and below this stair-step line. And all of these guys right here fit in this darkened line. So most of the elements are metals. Nonmetals are to the right and above this stair-step, right? They tend to be gases or brittle solids at room temperature. So a brittle solid, think of like a piece of charcoal. If you hit it with a hammer, it'll crumble. So now, just because there's not as many of them, it doesn't mean they're not important, because most of the things we find, though the nonmetals there are not that many of them, they're extremely common. Metalloids are on the line except for aluminum and polonium. So boron, silicon, germanium, arsenic, antimony, tellurium, astatine, sure, but it's very radioactive. Okay? They have intermediate properties, but we're not going to deal with them very much in this class. All right, so using a periodic table, see if you can figure out the answer is it's a metal or a non-metal. So look at the periodic table. Okay, like I said, I would have printed one out by now if it was me. Hit pause, try this on your own. All right, did you try it on your own? Now let's see how you did. So if you look on the periodic table, sulfur is a non-metal. Cobalt is CO, so you might want to use that alphabetical list as well. Calcium is a metal. Phosphorus is a non-metal. Iodine is a non-metal. Now, by the way, people talk about minerals. Minerals are actually ions, and we'll talk about that more when we talk about water. All right. Another thing we can do with the periodic table, so you see these numbers here, the row numbers here? Okay. The row numbers are going to tell you, okay, the periodic table, like I said, it's a map. So the numbers on the periodic table tell us things. Now, if you look at this one, you see the numbers, the A and B subgroups, the A's and then the 7B, 6B. That's an old way of doing it. We're moving away from that. So the new system is we just number the columns 1 through 18. So the row number here is the outermost layer. That's actually referred to as the period. So this is the first period, the second period, the third period, and so on. So everything in row 1, okay, the electrons are in the first layer, the outermost electrons. In row, say, 3, all the valence electrons are in the outermost layer, which is the third layer. In row 6, the valence electrons would be in the 6th layer. All right, just think of them as layers or shells is another term. The column number, will tell us the number of valence electrons, but it's tricky. It's the number in the ones place. So for example, hydrogen is in column 1. All of these have 1 electron in their valence. So for example, lithium, which is in row 2, column 1, would have 1 electron in the second layer. Okay? Calcium would have 2 electrons in the 4th layer. See how you can use the table? 4th layer, 2 electrons. Okay, now over here, how do we know? That doesn't have, if you look at carbon, it's the number in the ones place. So everything in column 14 has 4 electrons in the valence. Everything in column 16 has 6 electrons in the valence. All right, so try these on your own. Hit pause. All right, did you hit pause? Try them on your own. Let's see how you did. So silicon is in column 14, 4. Nitrogen is in column 15, it has 5. Fluorine is in column 17, so it has 7. Sodium is in column 1, so it has 1. Oxygen is in column 16, so it has 6. Now what I'm going to do is I'm going to stop here and for the end of video number 2, and then we'll pick up here for the next video.